Hi. So today I want to talk to you about enthalpy and finish up Chapter 1 in Schroeder's thermal physics. So what is enthalpy? Well, constant pressure processes occur all the time. Chemical reactions, for example, which are tabletop, occur at roughly constant pressure, roughly 1 atmosphere depending upon your elevation. So for gases at constant pressure, usually when there's a change in the temperature, that means there's a change in the volume too. And that means that in the expression for the internal energy, you always have to add in that compression and expansion work. So to make this a little easier on ourselves, we define the enthalpy. We use the symbol H to symbolize enthalpy. Most people assume that this is for heat, which we'll talk about in a few minutes. So here H, or enthalpy, is equal to U plus PV. So that's the sum of the internal energy U plus the pressure times the volume. Now, Schroeder's textbooks describes this total energy as the amount needed to create a system out of nothing and then put it in its environment. The PV part of that is the work that you have to do to move the air out of the way to make room for what you created. Of course, I also teach modern physics, so I have a disclaimer here, that's not really true. If you really wanted to create something out of nothing, then you'd have to have E is equal to mc squared, where you convert the mass directly from some amount of energy, and that would be literally nothing, no mass. The enthalpy is actually closer to the energy of the chemical reaction that you'd have to have in order to create the substance from the atomic building blocks which are already there and shove the air out of the way to make room. So it's assuming, this expression for the enthalpy, that you already have all the component atoms that you need to create your new molecule, for example, and they're sitting there waiting to react, which is a little different from out of nothing. But it's not a bad explanation, so we'll go with it. Now, just like any other kind of energy, lots of times we're not so interested in what the absolute value of it is, but rather a change when it goes through some kind of process. So for example, in introductory physics we talk about the potential energy of the system, but if you're talking about gravitational potential energy, for example, we're not so much interested in what it is at any given point in time, but any change. For example, if I drop it, what's the change in the potential energy as it falls? So the enthalpy is the same way. So we're going to talk about the delta H, or the change in the enthalpy of the system. So if I differentiate this little expression for H, U plus PV, then I would end up with delta H is equal to delta U plus delta P times V plus P times delta V. But I already said we're most interested in constant pressure processes. So I'm going to take that delta P as going to 0, and that leaves me with the expression for the enthalpy of delta H is equal to delta U plus P delta V. Now, I can plug in for what the internal energy is from the first law of thermodynamics. Remember, we covered that in an earlier lecture, and we said that any change in the internal energy of a system, delta U, is going to equal to the sum of the heat plus the work. So if I rearrange my equation for the change in enthalpy and write it in terms of delta U, then I have delta U is equal to delta H minus P delta V. Well, delta U is also equal to the heat plus the work, Q plus W, so I'll set it equal to that. Now let's consider all forms of work, so that the work would be equal to the compression expansion work, which is minus P delta V, then plus any other forms of work that I might have. That could be electrical work, like running current through a wire, or pretty much anything else. Okay? So now my work is going to equal to minus P delta V plus any other forms of work that I have, which I'll call work, W sub other. So now plugging in for that, I have delta U is equal to delta H minus P delta V. Subbing in, I've got that's equal to Q minus P delta V plus the work of other, which is that sum of Q plus W. Now looking at and rearranging and solving for delta H, I have delta H is equal to delta U plus P delta V, which is equal to Q minus P delta V plus any other forms of work plus P delta V. So my P delta V's cancel one another out, and I just end up with my expression for the enthalpy, which is equal to Q plus any other work that might be done. So now you can see maybe why we use H as a symbol for enthalpy, because you can see here that Q is a big part of it, the heat. So since the compression expansion work is already included in the internal energy, By speaking of the change in the enthalpy instead of a change of internal energy, we don't necessarily need to know or keep track of the compression expansion work. If no other types of work are being done on the system, then the change in the enthalpy will tell you directly how much heat, Q, has been transferred. Now, in an earlier lecture, we discussed heat capacity. We gave a nice expression for the heat capacity at constant volume, which was that C sub V is equal to the partial derivative of the internal energy with respect to temperature if you hold the volume constant. But our expression for C sub P, the heat capacity at constant pressure, was a little messier. So now I'd like to rectify that and put it in terms of the enthalpy. So if you find the heat capacity at a constant pressure, then you would have C sub P is equal to delta U plus P delta V, and then divided by the change in temperature delta T, held at constant P. Now, with a little bit of rearranging, I can sub in for what my delta U is. Delta U would be delta H minus P delta V, and then that cancels out with the plus P delta V. And so I end up with C sub P is equal to delta H over delta T, or if I shrink my deltas down to small, then I have a differential, that the heat capacity is the partial of the enthalpy with respect to the temperature with the pressure held constant. And this is a neater, more convenient way to refer to the heat capacity at constant pressure. Now, all of this talking that I've been doing over the last couple of slides actually demonstrates that the enthalpy changes as you raise temperatures of substances or take substances through phase changes. Basically, any time heat or other work is added, you have a change in enthalpy. So, for example, water freezing or water boiling, that would result in a change in enthalpy of the substance because you have to add or subtract heat in order to get those phase changes to take place. You also have to add heat if you want to heat water up from, say, 20 degrees Celsius to 50 degrees Celsius. So that would result in a net change in enthalpy of the system. But you also have changes in enthalpy during chemical reactions because heat has to be added or taken away in order to make or break bonds. So let's talk a little bit about the enthalpy of formation. Now, in Schroeder's thermal physics, at the end, there's a whole section called reference data. And if you look through and flip through those, which start on page 404 or 405, you'll see that there's numbers for the enthalpy of formation. There's also Gibbs free energy, which we haven't gotten to yet, and a few other numbers. But for now, let's just stick to enthalpy of formation. So those are usually symbolized with a delta H, and sometimes with a subscript of an F to indicate the enthalpy of formation, to distinguish it from the enthalpy of combustion, which we'll talk about in just a second. Now, the enthalpy of formation is the energy that's required to form the molecule listed in the table out of its elemental component parts. Consequently, if the substance is already in its pure standard state, then the enthalpy of formation is 0. Now, your tables in the back of your book specify enthalpies of formation for a very specific set of circumstances. The ones in Schroeder specify it for a temperature of 298 Kelvin at 1 atmosphere of pressure, 1 bar of pressure, which is a little bit less than an atmosphere, and if you have 1 mole of a substance. So of course, if you change those conditions, if you change the temperature away from 298 Kelvin, for example, then the enthalpy will change a little bit as well. And if you're looking at a different set of tables, then you might see slightly different numbers if those tables are listed for different temperatures, for example. Okay? But if the substance is in its pure standard state, given those conditions I just described, then the enthalpy of formation is 0. Often, the tables will also specify the phase that the compound is in, because, as we just discussed, you have to add or subtract heat in order to get the substance to go through a phase transformation, and so the enthalpy will change if that happens. Now, as an example, the table in Schroeder lists hydrogen gas, H2, as a gas, and the enthalpy of formation for that would be 0, because that would be its natural state at 1 mole and 1 atmosphere pressure and 298 Kelvin. It would be a diatomic gas. Okay, so here's a little excerpt from the tables that you can see. You might be able to zoom in and take a look at them. But if you can't, you can open up your textbook or find a similar table and it'll tell you pretty much the same thing. Now let's examine for just a second the reaction for water. So a reaction for water would be if you take hydrogen gas, H2, and then add in a half mole of oxygen gas, O2, then that would yield H2O. So that would be how you would write that chemical reaction. If you look at the values in the table to the right for this reaction, hydrogen gas and oxygen gas, when it's diatomic and a gas form, are already in their natural states. And so the enthalpies of formation for those things are both 0. But if you look at water, the enthalpy of formation for liquid water is minus 286 kilojoules roughly. Okay, now you can look at that now and write the enthalpies of the reactants on the left and the products on the right, and you get 0 plus 0 yielding minus 286 kilojoules. Now this is the change in the enthalpy during the reaction. It implies that the enthalpy has dropped once the water is formed. Now what this means is that heat has been given off, because you start off with more heat, right, 0 on the left-hand side, and you end up in the negative on the right-hand side. So this is an exothermic reaction. Exothermic reactions give off heat, so the enthalpy should be lower on the product side. So forming bonds is generally exothermic, right? Because you've got a certain potential energy for the things in their pure form, and then when they bond, the potential energy of the system will drop. And so when that happens, heat has to be given off, and that's exothermic. The other kind of reactions are endothermic reactions. They take in heat. So if you're writing, figuring out what the enthalpy is for that, then the enthalpy should be higher on the product side than it is on the reactant side. Now in general, breaking bonds is endothermic because it takes energy to break them. And of course, forming bonds is exothermic generally. But we'll talk a little bit more about endothermic and exothermic when we get to Gibbs and Helmholtz free energies in a later chapter. For now, let me do an example problem. And this example problem is, we're going to use the data at the back of the book and the tables to determine the enthalpy of combustion for 1 mole of glucose. So if you write that reaction out, it's C6H12O6 plus 6 diatomic oxygens yields 6 carbon dioxides plus 6 waters. So this is the net reaction that provides most of the energy needs in our bodies. So in other words, we take in food, we break that into little molecules, it's absorbed by the blood, we burn it, we burn that glucose, and then we have the energy that we need to do all the tasks that we do throughout the day. If you go to the tables and look up the enthalpies of formation for both the reactants on the left and the products on the right, then for glucose you get negative 1273 kilojoules, but oxygen is already in its pure form, so that's 0. So then on the left-hand side you have negative 1273 plus 0 is equal to negative 1273 kilojoules on the left. Now on the right we have 6 carbon dioxides. So the enthalpy of formation for carbon dioxide is negative 393.51 kilojoules, but there's 6 of them. So you have to multiply that negative 393.51 times 6. You also have 6 waters. Waters, as we already discussed, is negative 286 kilojoules. Actually, it's negative 285.83, so I went ahead and wrote that out. But yet again, you have 6 of them, so you have to multiply that number times 6. So if you sum up on the right-hand side, you get 6 times negative 393.51 plus 6 times negative 285.83, and you end up with negative 4,076.04 kilojoules on the right. Now you can see here that on the right-hand side, the enthalpy is lower than it is on the left-hand side. So this is an exothermic reaction. If you subtract these sides, we can see that delta H is negative 2,803.04. Okay? If you want to figure out what the enthalpy of combustion would be, then you have to take the absolute value of that number, and it's plus 2,803 kilojoules. Okay, I hope that helps. If you have any further questions, I'll see you in class.